Good morning, everybody. Today we will continue with the X-ray diffraction. During the last week, we have seen details of X-ray diffraction, some important steps in X-ray diffraction. Now we will give you some real examples of X-ray diffraction, and I will try to calculate the position of the peaks and Miller indices of the crystals. And we will also talk about in-plane X-ray diffraction and its difference from the conventional out-of-plane X-ray diffraction. So the application of X-ray diffraction, maybe first of all, I should choose laser pointer. Okay. So the application of conventional X-ray diffraction, usually called as high angle X-ray diffraction or wide angle X-ray diffraction. In many books, you can see these different names: high angle X-ray diffraction, wide angle X-ray diffraction, or high angle Bragg scattering. You can see all of these names. You know why the Bragg name is used here. We have explained during the last lecture. So for application of out-of-plane X-ray diffraction, another name is out-of-plane X-ray diffraction. So you can see that there are more or less 4 names defining the same experimental method: high angle X-ray diffraction, high angle Bragg scattering, wide angle X-ray diffraction, or out-of-plane X-ray diffraction. You can meet all of that names and explanations in the books and papers. So what is the importance of that method and what we can get by using that method? So we have 3 main targets. By using that method, we can determine the crystal structure. Is it cubic or tetragonal or hexagonal? If it is cubic, BCC or FCC. We can also determine the direction of the crystals. Okay, we can determine the Miller indices by using that method. And we can determine the defects in the crystals. In addition to that, this method is non-destructive. So you investigate your material and it is not destroyed. It is very important. So very helpful, very fast, a very accurate method. So first of all, let me remind you crystal structures. Actually, you have seen all of this information within your previous lectures, mainly in solid physics courses or condensed matter physics courses. So here, let me summarize. There are 7 crystal classes here: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, triclinic. These are the 7 crystal classes. 1, 2, 3, 4, 5, 6, 7. 7 crystal classes. And here within these crystal classes, we have 4 types of unit cell. So here we have primitive unit cell shown by blue color. Okay, these are the atoms on the corners and nothing on the surfaces, nothing in the unit cell. This is called as primitive cell. And here we have this green colors, body-centered unit cell. What we see here, atoms on the corners and 1 atom in the center of the unit cell. And here we have this red color. We have face-centered unit cell. What we see here, we have 8 atoms on the corners and also 6 atoms on the surfaces of the unit cell. This is called as face-centered. In addition to that, there is side-centered, which is shown by that color, I think purple or violet, I'm not sure. So what we have 8 atoms on the corners, and in addition to that, we have 2 more atoms. Okay, so this is called as side-centered. So each crystal classes have some of them. So look at the cubic one. cubic crystals have primitive body-centered and face-centered unit cells. If you look at orthorhombic, it can be in the form of simple unit cell, body-centered, face-centered, and site-centered. So others, this one has only primitive, primitive, primitive, primitive. This is also can be in site-centered form, okay? So in total, 7 crystal classes and 4 types of unit cell. So let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in total, we have 14 Reveus lattices, okay? So you already know that information, but I would like to summarize it for you. But in applications, usually many crystals are in the cubic form, okay? Body-centered, face-centered. Tetragonal is also very widespread, and hexagonal is also widely used. So we will talk about some of them. So now let's talk about Miller indices. So Miller indices defines as the surfaces of the crystals. Here you see a cubic cell, let's say. So this is the direction of the X, this is the direction of the Y-axis, this is the direction of the Z-axis. So what are the names of the surfaces? So, and how to determine this one? So during the last lecture, we have seen that we have interplanar distance, and this interplanar distance is shown by the subscripts HKL, okay? So how to calculate this HKL? We have learned how to calculate D, but how to calculate this HKL numbers? So H is associated with X-axis, K is associated with Y-axis, and L is associated with Z-axis, if you consider that coordinate system. So how to determine the name of that surface? Look at this one. So you do like this. So this surface intercepts the X-axis at infinite, right? And this surface intercepts the Y-axis at infinite, and this surface intercepts the Z-axis at 1. So 1 over infinite gives us 0, 0, 1. So this is 1001 surface. The name of the surface is 001. The direction is given by 001, okay? Direction of crystal along the Z-axis. So if you look at that surface, for example, what we have here, it intercepts at 1 along the X-axis, 1 over 1, and intercepts both Y and Z-axis at infinite. Then we have that surface, okay? So same for this one. So this is how we calculate the Miller indices. Now let me clean them, and then I will continue with other surfaces. So let's continue with, for example, that surface. What do you see here? We have a surface like this. It cuts the X-axis at 1. It cuts the Y-axis also in 1, but it is always parallel to the Z-axis. Never intercepts the Z-axis. So 1 over 1, 1 over 1, and 1 over infinite for the Z-axis, and then HKL numbers are given by 1, 1, 0. Okay, so actually it is not complicated. So maybe you can also look at that surface. So here we have already done it, I think, during the last lecture. This is given by 111. And here you can see some uppercase here, and also here. This shows that they cut the x-axis in negative x direction, and also for this one it cuts the y-axis also in negative direction. You can also show that surfaces like this, you can see that, for example, this one can also be shown like this. Okay, this one can also be shown like this, but this is much better representation of the surfaces if they cut the x, y, z axis in negative direction. Maybe I can show you one example here. So let's consider that this is y-axis, this is x-axis, this is z-axis, and here we have a cubic structure. Okay, so let's continue a little bit on the negative side. Okay, so this is 0. This is unit cell, so this is 1, and this is -1. So if you would like to calculate name of that surface, it cuts the x-axis at -1, 1 over -1. It cuts both y and z axis at infinite, because this surface is parallel to both y and z axis. So here we have that relation. Then the name of that surface is -1, 0, 0. Okay, like this. So let me clear again. Do you have any question in that part? If not, I will continue with the hexagonal crystals. So X-ray diffraction method allows us to determine these surfaces of the crystals. Okay, you grows a crystal by using different methods. Okay, in vacuum conditions or with some other methods, and then you would like to learn that which direction of the crystal is preferable within your thin film or material. Then X-ray diffraction can determine it for you. So let's have a look. Miller indices of hexagonal crystals. What do you see here? We have 4 HKL numbers, or we have 4 Miller indices here. Okay, compared to the cubic ones, we have here 3. Okay, here we have 4 numbers, you see? So what is the meaning of that 4 numbers? So in cubic crystals, we have just HKL numbers. But in case of hexagonal crystals, in order to separate them from the cubic crystals, we have these numbers, H, K, L here. But in addition to that, minus H plus K we have as a third number, okay? For example, look at that surface. Look at that one. What is this? Actually, you can also write this one like this. H is H, K, L. Okay, you can write this one like this, 1, 0, 0. Okay? But then, what is 1, 0, 0? This surface, okay, in cubic crystals. So how to separate them from each other? This is cubic, this is hexagonal. So in order to separate from each other, then we have this type of representation. 1, 0, minus H plus K with negative sign. It is -1 and 0. Okay, or you can show it like this. as it is presented here. So look at this one, 1, 1, minus 2, 0. So in hexagonal crystals, it is like this. In addition to that information, in hexagonal crystals, we have different predefined surfaces. Let me also talk about that surfaces. Here we have M plane, here we have C plane, here we have A plane. You see that? And C plane is this one, this basal plane here. And it is widely used in hexagonal crystals. So let me show you in total structure of the hexagonal crystals. It is like this. Okay. So you can see, consider that this is hexagonal crystal. So this surface is given by that name. It cuts the z-axis only. Okay, so the name of that surface, this is the direction along the z-axis. So if the crystal grows like this is called as C-plane, okay? So A-plane shows us that surface, very common surface of hexagonal crystals when you grow them by using thin-film preparation methods. So where does this surface we have? Let me choose another pen here. So if you take, let me choose the color. If you take this one, okay, this surface here we have, okay. So this is the information on Miller indices of hexagonal crystals. If you have any question, please let me know. Because within that lecture, I will show you one example related to the hexagonal crystals. So let's continue. We have already learned that information during the last lecture. I will not go into detail today. So what we have here, we have DHKL and we have different crystal classes, cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, it goes. And here we have rhombohedral, okay? So then we have the HKN numbers, and this is the most common one. This one, and this one are the most common ones. So at least I strongly suggest you to keep this one in your mind, okay? Sometimes it is maybe not so easy to keep that formulas in your mind. You usually check from the tables, okay? When you are investigating your crystal. But for the exams, I strongly suggest you at least to keep that one in your mind. So this is given, is this one. Very easy to keep in your mind. Square of all Miller indices and square of the lattice parameter. That's all, okay? You can keep this one in your mind. So let's continue. How to carry out X-ray diffraction experiments. I will not go into detail about the production of X-rays and also X-ray detectors. I have already spent one lecture or two lectures on how to produce X-rays in conventional laboratory X-ray diffraction machines. Usually X-ray tubes and rotating nanotubes have been used, okay? So here we have an X-ray tube with radiation shielding, okay? So here we have a detector, scintillation counter, gas ionization chambers, proportional counters. What else? Geiger counters, semiconducting counters and CCD counters can be used instead of detector here. Okay, we have seen many detector families in the past, in the previous lectures. So here we have X-ray source, here we have X-ray detector, and here you see a table, okay, for the sample. You can put your sample here or your thin film here. You can put very small sizes of samples, or you can also use huge wafers, okay, with up to 5 centimeters. And what you see here, this is many axis goniometer. During the last lectures, I have talked about the goniometers. So goniometers are devices which with multi-axis freedom. You can hold the system by using computer program, okay? So here we have one axis for the X-ray source, another axis for the X-ray detector. Here we have one more axis to completely rotate that one along that axis. And here we have Eulerian cradle, okay? You can move all that stage around this axis, and you can also move the sample in and out. You can manipulate the sample in other angles, okay? So here we have at least 5, 6 freedom of axis, okay? So very useful conventional X-ray diffraction machine. So X-ray diffraction experiments have been carried out by using such instruments in the laboratory, okay? At the university, in research center, you can use them. But if you would like to use very high intensity and monochrometers, you have to go to synchrotron radiation sources. We have given you very much detail on synchrotron radiation sources. I will not repeat them here again. So then let me continue if you don't have any question here. So now let's consider that you have measured your sample, and then you get this data. This is the 2 theta axis, and this is the intensity recorded by the detector. So this is taken by conventional theta 2 theta measurement, or theta 2 theta measurement, okay? So you rotate the X-ray source and detector simultaneously, and detector angle always must be 2 times higher than the incident angle or sample angle. I have discussed all these things during the last lecture. So you change the position of the sample and detector, I mean 2 theta, okay? And then you send the X-rays and record the intensity within the X-ray detector. So this is the intensity recorded by the detector. So here you have a signal, okay? So how to analyze that signal? This is very important. So this measurement takes more or less 1 hour, okay? It depends on your needs. It depends on the range, okay? So within 1 hour, or this alignment within, let's say, half an hour, so you get that type of signal. But what this peaks, what this intensity, what that angles tell you, okay? So what is the information here? How to get that information? So now I will show you. So here, if you have such signal, such X-ray diffraction signal, 2 important things you have to consider. One is Brecht's law, and lambda to the sinus theta, HKL here, okay? This formula will give you a lot, okay? By using that formula, you can explain many features here. And the second thing is that intensity, okay? By using the intensity information and by using the Brecht's law, you can analyze that signals, okay? Don't forget this. So now let me clean and continue. So what to do. Here we have one peak here. This is the position of the peak. Let me show you like this, and another peak here. So what also you see here, that this is a much broader peak compared to that sharp one. So without doing any calculation, you can consider that this sharp one comes from the substrate or single crystalline very thick layers. Okay, this comes from the substrate, this sharp one. Okay, in high angle X-ray diffraction, and this broader one with this satellite oscillations on both sides comes from thin film, but with very good crystalline quality. Okay, so so depending on the position of the peak, for example, here it is around 34.2, something like this, 2 theta. And here 2 theta number is around, let's say, 37.8, something like this. Okay, so first of all, determine the 2 theta and determine the theta, half of it. And then calculate sinus theta, because we will use it within that Bragg's formula. Okay, so you have determined the sinus theta from that position of the peaks, put the sinus theta here, and then you know the lambda, because the wavelength of the X-ray source is fixed. You know the lambda, put that lambda here, and by using the sinus theta information which you get from the data, you can calculate the HKN number. You can calculate this. So if this is cubic structure, then put that HKL number. If you know the lattice parameter, you can calculate HKL numbers. If you know the HKL numbers, if you know the surface name, then you can calculate lattice parameter of the crystal, okay, by using that information. So Bragg's law helps us a lot, okay, in order to analyze that kind of X-ray diffraction results. Do you have any question in that part? Let's continue with a real example. Here, I show you a real measurements. The red one here, this one is taken in Hamburg at Hazelab, Hamburg Synchrotron Laboratory. I think it was taken in 2006, something like this, 14 years ago. And here we have 4 more measurements. They are taken in Dortmund, in Delta Synchrotron Radiation Facility, Dortmund Electron Accelerating Center. So in Hazelab, this data is taken with the energy of 8 kiloelectron volt. The wavelength is around 1.5 angstrom, 1.54, and this data is taken with the energy of 11 kiloelectron volt. So wavelength is a little bit lower than this one. In order to show them in a single X scale, we are using Q formula. I have discussed what is that Q during the last lecture. This is given by that expression. Q is equal to 2 pi lambda sinus theta, right? So let's consider that you have a data which is taken by X-ray diffraction. This is intensity, comes from the detector. This is the x-axis 2 theta, okay? So you have measured that signal, and you have measured this one with another. So let's consider that you are taking 2 measurements by using 2 different wavelengths. So let me talk about it a little bit more, because this is important. Let me choose another pen here. So the blue one, let's say, taken in Delta, and the red one is taken in Hazelab, okay? So if they have same energies, then you can show them together like this. But since the energy of the X-rays and energy of the X-rays in different centers, they are different, so then they will not be like this. Okay, you cannot present them in a single graph. So in order to present them in a single graph, you have to make that conversion. Instead of theta, just use that expression. So calculate sinus theta from this one, and then put it there. Then you will get Q here. Okay, in Q scale, you can represent both data taken in different synchrotron sources with different wavelengths. So for this reason here we use Q. Okay, this is 1 over angstrom because lambda is given here in angstrom. So any question here? Then I will go into detail about the signal. Now let's have a look at the sample. Here we have sapphire, aluminum oxide. Okay, it is 1,1-2,0, single crystalline sapphire, in very good quality. And here we have zinc oxide. Zinc oxide grown by sputtering method. It is very thin, 30 nanometer. Okay, the thickness of this guy is about 0.5 millimeter or 1 millimeter, let's say, and thickness of this one, zinc oxide, is around 30 nanometer. And I don't know its orientation. Then I send cobalt ions into the zinc oxide by using ion implantation. It is like bombarding, okay? So you send very energetic cobalt ions by accelerating them, okay, with ion implantation method. You send them into the material, okay? And they have 40 kiloelectron volt energies, and they can pass through zinc oxide, and they can enter into the sapphire, depending on the thickness of the zinc oxide here, okay? So first of all, at the beginning, we have just sapphire and zinc oxide. We don't have any cobalt ions, just sapphire and zinc oxide. And then we characterize this one, pure zinc oxide, nothing inside, no cobalt, right? Then we have measured that signal, pure zinc oxide, measured at Hazelab. So what we have here, we have very sharp peak. I know that this comes from the sapphire because it is very sharp. Sapphire is thick and single crystalline. It will give such a peak with, you can consider that it looks like delta function, okay? So I know the orientation of the sapphire, but you can also calculate from the position of the peak. So, but from that one, you can calculate 2 theta, theta, sinus theta, and by using the method here, which I have explained, you can calculate Miller indices of the sapphire here. 1,1-2,0 surface, okay, aluminum oxide, sapphire. So what about zinc oxide? Here we have an additional peak. So this comes from the zinc oxide. So here you see oscillations, you see. These are called as low oscillations, which show the quality of the crystal structure of the zinc oxide. Okay, it is grown with very nice crystalline quality. This oscillations, low oscillations showing that. So now I implant this system by using cobalt ions. So we send cobalt ions into the system. And I would like to learn that what happens if I increase the number of the cobalt ions or density of the cobalt ions or dose of the cobalt ions within the material, okay? Energy of the cobalt ions are fixed, they are accelerated and bombarded or sent into the material. So now here we have many questions. So cobalt ions are stopped in zinc oxide, or they are allowed to go into the sapphire. And what about the cobalt ions? They are sitting in the crystal structure like this. For example, one cobalt ion comes and then replaced by that atom, okay? It comes instead of that atom, and this is taken out, okay? So this is substitutional case. Or atoms are collected within the zinc oxide and form clusters. Or atoms can sit on the sapphire crystal, or they can form clusters within the sapphire, okay? So I don't know the answer of that questions. I would like to learn, okay? So any other question concerning this one? So the other question is, what about the damage of the zinc oxide? On the surface of the zinc oxide, is there any damage or not? Or what about the damage in the sapphire due to the implantation? Okay, you can consider that you are shooting the wall, okay? You are shooting the wall by using gun, for example. So then you will destroy it, okay? These are very energetic cobalt ions. You can destroy the surface or crystal structure of the zinc oxide. What about this one? So we wonder all that questions, okay? We don't know it. So this was the pure one without implantation, without no, we don't have any cobalt here in that case. Then here you see numbers, 0.75, 1, 1.25, 1.5. These are showing that we increase the cobalt concentration within the material, okay? So what you see here, we have zinc oxide peak on the left side, we have sapphire peak. What you see here, we have an additional peak, which was absent here. And you increase the number of the cobalt ions, again, zinc oxide peak, sapphire peak, and this peak here becomes more clear. And you increase the number of the cobalt ions, then finally you get that signal. So what do you see here? We have lots of information here. So the first one, the position of the sapphire, okay, it is fixed. It is staying at the same position. Sapphire position is fixed. But what about the zinc oxide position? Look at the zinc oxide position. Zinc oxide position changed. But you see here that the position of the peak, you see, it goes to the right side. So what about that information? So one information here, the position of the zinc oxide, one information. Another information here is that what you see here, the intensity of zinc oxide is very good before implantation, but after implantation, what do you see? That the oscillations are lost and intensity also decreased. You see, if you look maximum and minimum intensity of zinc oxide for each measurement, so intensity decreased, delta I decreased. This is the second information. Okay, I should talk about this. And what do you see here? That we have just this type of signal, but after implantation, I have a shoulder on the left side of the sapphire. Okay, this is third information. What else? Here I have an additional peak. This is the fourth information. I can get at least 4 types information from that measurement, X-ray diffraction measurement. So what about this one? Why the position of the zinc oxide peak changes? So let's consider that this is 2 theta axis, okay? This one is 2 theta axis. So at the beginning, the position of zinc oxide was here, and it moved to the right side. Then Breck's law will help us, n lambda to the sinus theta. So if the peak moves to the right side, it means that sinus theta is increased. Since the left side is fixed, it means that this DHKL is decreased. So zinc oxide is a hexagonal crystal. Okay, here we have 001 direction. So it is grown like this on the sapphire. Okay. This is the 001 surface of the zinc oxide. So what do you see here, that this, the 001, I mean interplanar distance between that planes, okay, is decreased, okay? Lattice is shrinked. Interplanar distance is decreased after ion implantation. Before ion implantation, I have normal structure of the zinc oxide, and after ion implantation, this peak goes to the right side. So why it happens? Then I should investigate this one. Let's have a look. This periodic table here. This is the zinc, okay, and this is cobalt. What you can see here, that zinc is bigger atom than the cobalt, right? Whenever you put smaller cobalt atoms into the zinc oxide, so let's consider that here at the beginning you have huge zinc atoms compared to the cobalt atoms, okay, like this. But then you put smaller cobalt atoms and they are replaced by the zinc atoms, okay? Then the D interplanar distance will be decreased. Then sinus theta will be increased and peak will move to the right side. So what it tells us, this information tells us that some portion of the implanted cobalt ions entered into the zinc oxide and they are sitting on the zinc oxide crystal structure. Okay, this is first information we can get from that signal. Any question? This is the first one. So the position of the peak tells us that. Soru mu var?
Affedersiniz hocam. Şu 1, 2, 3, 4'lü koşulları yeniden söyleyebilir misiniz kısaca?
Of course, the first one tells us that the position of the zinc oxide, this is zinc oxide, okay? This is the position for zinc oxide 001. So it moves to the right side after ion implantation, okay? After ion implantation, the position of that peak moves to the right side. The second one is that here the intensity is very nice before ion implantation. You see intensity difference between the peak and background signal, but here intensity is bad, okay? Intensity is decreased. Why intensity decreased? Okay, this is question. And before the ion implantation, here we have more or less symmetric signal from the aluminum oxide, from the sapphire. But after ion implantation, we have an additional feature. What is the reason of that? The first one is we have nothing here in pure zinc oxide, but after ion implantation, I have an additional peak here. What is the reason for that? Okay, this is the explanation of the features, or these are the questions which we have to answer them. So now let's come to the second one. We have already solved the first one. We have any question, Mergim?
Yes, I have a question. If cobalt atom replace the zinc atom, so
Yes.
it will occupy the less space compared to zinc, right?
Yes.
And shouldn't be the distance between them shouldn't be increased? I can't understand how the D decreased because of the substitution.
Okay, so let's consider that. Let's consider that you have bigger atoms. You have bigger atoms. And you have this type of arrangement of the atoms, okay? So interplanar distance, let's say, for that surface is this one, okay? You can consider like this. So here you have one plane. Here you have another plane of atoms, and this is the interplanar distance. But if I, let's say, remove that big atoms and use smaller atoms, for the same crystal structure, the interplanar distance will be less compared to that one, okay? So what happens here? Here within that zinc oxide, not all of the atoms are replaced by the cobalt atoms, but only some portion of them replaced by the cobalt atoms. So now instead of a big, let's say, zinc atom, we have cobalt atom. Here again, instead of a big zinc atom, we have another smaller cobalt atom. Here again, we have another smaller cobalt atom instead of big zinc atom. But in total, okay, what you see here that I can draw like this. Okay, in total, this D interplanar distance decreased a little bit, okay? So I can see it here. So zinc oxide zinc oxide has hexagonal crystal structure, and this interplanar distance, okay, the interplanar distance here for one surface is decreased a little bit because some portion of the zinc atoms in the hexagonal crystal structure is replaced by the cobalt atoms. Is it clear, Mergim, now?
Yes.
Okay. If not, please let me know, then I can try to explain in other way.
How about when we think about the hexagonal structure? You draw the bigger atom upside, and how let's say we change the zinc atom the bottom line. So
actually I didn't understand your question.
Türkçe söylesem daha iyi belki.
Okay, please.
Siz hexagonal yapıyı biraz evvel gösterdiniz ya. Mesela bir köşedeki zinc atomu olsun. Aşağıda da ya sadece bu üst plane'i mi düşüneceğiz?
Yok. No, not like this. Okay, I understand now. So let me draw. Good question. So the thickness of zinc oxide is about 30 nanometer. Okay, what about the size of one unit cell of the zinc oxide? C parameter here about 5 angstrom, okay? So 30 nanometer means that 300 angstrom, okay? We have many zinc oxide layers, okay? And we have many hexagonal crystals. They are arranged like this, okay? Many of them, maybe 100 unit cell layers you can consider. Okay, let me also draw like this. I'm looking from the side, okay? So let me also finish that part. Okay, so when you implant this cobalt ions, some cobalt atoms sits here, some of them sits here, some of them sits here, some of them sits here, okay? But in total, the D parameter, DHKL, D001 of the zinc oxide crystal is shrinked, okay? D is decreased in total. I mean, the cobalt atoms can reach in every part of zinc oxide, okay? So we have many cobalt ions on the lattice of the zinc oxide, not only top surface. Is it the answer of your question?
Yes.
Okay. Any question here? Then let me continue with the second feature here on the X-ray diffraction curve. So what the second feature tells us. Here we have seen that before the ion implantation, the intensity is nice here, okay? Delta I, background signal, and this is this intensity in the maximum position of the peak. But here at the end, delta I is smaller. And indeed, it gets smaller, okay? If you go like this, if you increase the cobalt concentration, intensity goes down. So what happens? So we have understood the first feature, why the position of the zinc oxide peak changes. We have explained this one, and why intensity also decreased. Intensity, what was intensity? So here you have a thin film, and here we have an X-ray source, and here we have a detector. So this is the intensity recorded by the detector. So intensity is decreased after ion implantation, intensity of zinc oxide. It means that less X-rays come to the detector. But why? Why this film sends less X-rays? The answer is that we destroyed the surface and crystal structure of the zinc oxide. Since we destroy it, it cannot behave like perfect mirror, okay? You can consider that you have a destroyed mirror in your bathroom, okay? So it will provide you much less intensity compared to the perfect mirror with perfect alignment of the atoms, okay? You can consider like this. So let's consider this condition. Before ion implantation, before cobalt ion implantation, let's consider that the surface of the zinc oxide is perfect. Atoms are periodically arranged, and I have perfect surface, like a perfect mirror, and each incoming X-ray goes to detector, okay? But after ion implantation, what happens? I have this type of surface. So what do you see here? Also within the material, everything is destroyed. Okay, so here you have a perfect surface before the implantation, but after the implantation, you're not. So incoming X-rays cannot go to detector. Only very few portion of them can go to detector since the material is destroyed. It is behaving like a destroyed mirror. Is it clear? Okay. Then I consider that you don't have any question with that part. Let me continue with the third feature.
Teacher, the distance in atoms is getting much after
no, after ion implantation, the distance between the planes of the zinc oxide getting less. Okay, so the crystal structure, the lattice is shrinked for the zinc oxide after ion implantation. This is related to the first condition, but in case of second condition, we have destroyed the crystal structure of the zinc oxide. We have produced we have produced damage on the surface of the zinc oxide. Okay, for this reason, we get less intensity after ion implantation. This is related to the second one.
Okay, thanks.
Okay, so now let's have a look the third feature here. Why we see a shoulder on the left side of the main peak of sapphire. So, and what is the meaning of that? This third feature here, shoulder on the left side of the sapphire peak, tells us that some portion of the cobalt ions are located within the aluminum oxide substrate. So at the beginning, I have asked that question. I have implanted this material by using 40 kiloelectron volt energetic cobalt ions, and they can reach to the sapphire or not. Okay, and this data tells us that they can reach to sapphire. Okay, this data here tells us they can reach into the zinc oxide, and they produce some changes on the crystal structure and also the intensity of the zinc oxide, but they can also reach to the sapphire. This data tells us. But what else this data tells us? Let me also discuss these things. What else we see? This feature becomes dominant and visible with increasing cobalt concentration, right? So what is the meaning of that? It means that some portion of the cobalt sits on the sapphire or aluminum oxide lattice, and the aluminum oxide crystal structure is expanded. Aluminum oxide is hexagonal again, okay? So what is the expansion? So look at the position of the initial aluminum oxide peak. It is here. Now this peak went to the left side, okay? So if you look at the Brecht's formula to the sinus theta, now we have smaller theta, right? Because the signal, just always keep this one in your mind. Sinus theta, if this is increased, then if this is decreased, this is also decreased because this is constant. If this is increased, this is also increased, okay? So what we see here, that here we have feature on the left side. So then sinus theta is decreased. It means that D is increased. What is the meaning of that? Sapphire is laying like this. Let's consider. Okay. this is the -2 surface of the sapphire, and then we put zinc oxide on top of it. Zinc oxide is produced like this. Okay, with that one. So if you implant this system with cobalt ions, some cobalt ions sits on the zinc oxide lattice, and some of them sits on the sapphire lattice. Is it clear? So what happens to the sapphire lattice? Look at the periodic table. Aluminum here. Aluminum is smaller than the cobalt, right? Here at the beginning, within the sapphire, within the aluminum oxide, we have smaller atoms like this one. Let's consider that these are the aluminum atoms at the beginning. And after ion implantation, I have much bigger atoms, which are cobalt atoms, okay? Cobalt atoms are much bigger than the aluminum. Then what will happen? This bigger cobalt atoms will expand the unit cell of the sapphire. Then sinus theta will be decreased, and we will have an additional peak in lower angles. Is it clear? We have one more information related to the sapphire. This is the fifth one. 1, the position of the zinc oxide. 2, intensity decrease in zinc oxide. 3, shoulder on the left side of the aluminum oxide. 4, why the position of the zinc oxide does not change, or let's say this is fifth one. And 4, why we have an additional peak here. So now let's continue with the position of the aluminum oxide. What we have seen here, that the zinc oxide peak position was here at the beginning, and after ion implantation, it moved to the right side. We have explained this one due to the lattice shrinking of the zinc oxide, okay? And here we have an additional peak, but now on the left side of the original position of the aluminum oxide, we have explained that this is due to the lattice expansion of the sapphire, okay? But here we have seen that this zinc oxide peak completely moved to the right side, okay? But here we have seen that the mean peak of the aluminum oxide is preserved. It is fixed. It has been fixed its old position. In addition to the main peak, we have seen an additional shoulder here. So why this main peak is preserved in its old position? Because this fifth information from that data tells us that cobalt atoms cannot reach to all parts of the sapphire. They can only be implanted close to the surface or interface between zinc oxide and sapphire. So they can enter and they can pass through the zinc oxide, but they cannot go further, okay? They lose their energies within the sapphire, okay, here. So the most part of the sapphire does not contain any cobalt. For this reason, we can see main peak of the sapphire here, okay? Sapphire is not damaged, or the properties of the sapphire are not changed by the cobalt atoms, because in most part of the sapphire, we don't have cobalt. Cobalt atoms cannot reach to the many parts of the sapphire. They are only located within the sapphire, close to the zinc oxide sapphire interface, okay? But of course, also we have many cobalt atoms within the zinc oxide, okay? Cobalt atoms are located here in that region. They are completely distributed into the zinc oxide, but also a very small part from the sapphire are influenced by the cobalt atoms. This is the explanation of the fifth information from that signal. Let's continue with that fourth information. Okay, here, why we see an additional peak here. What is the reason for that? At the beginning, we have nothing in pure zinc oxide, but after ion implantation, we have an additional peak, and the intensity of that peak gets bigger. Okay, so what is the reason for that? This is related to the cobalt. Cobalt is hexagonal, and for this reason here again we have four numbers, 1 O minus 1 O. Okay, so we have some cobalt clusters and they form their own crystal structure. What we have discussed here for this case, and cobalt atoms, implanted cobalt atoms, sits on the lattice, okay, replaced by the host material atoms. But some portion of the cobalt atoms form their own crystal structure, formed from completely cobalt atoms. Okay. They are also in hexagonal structure. Okay. So cluster means in Turkish kümelenme. How can I explain in better way that the cobalt atoms are not staying on the crystal structure of the zinc oxide, and they are not located within the crystal structure of the sapphire, but instead they form their own crystal structures and they produce clusters, okay, like ghettos, okay, in the cities. So you can consider this one. So they are not distributed homogeneously. Some part of them produced clusters. So what you have learned that just this 5 measurements, this one, first, second, third, fourth, fifth. So by using 5 X-ray diffraction measurements, we can get a lot of information about the structure of zinc oxide and sapphire and the position of the cobalt and damages on the surface of the zinc oxide and the crystal structure after the ion implantation within the zinc oxide. We have learned all the things by using X-ray diffraction, okay? And we did not damage the material, okay? Because this method is non-destructive. So this is the power of the X-ray diffraction method, okay? You can get many information. So just by doing 5 measurements. So very few methods can give you that information, okay? For this reason, the X-ray diffraction is very useful. Here we have more or less the same case. Here we have titanium dioxide rutile. Rutile is a different crystal structure, but in general, you can consider that this is within the family of tetragonal crystals. And we implant that titanium dioxide with cobalt ions, okay? So what happens? This is the pure titanium dioxide without ion implantation. After ion implantation, we see a shoulder on the left side, okay? After cobalt ion implantation, we see a shoulder on the left side. And at the beginning, we have nothing here. We have nothing here. After ion implantation, we have this huge peak. And we have some additional peaks here. You see, at the beginning, we have nothing. After cobalt ion implantation and increasing the cobalt ion implantation dose, we see some additional features. 1, 2, 3, 4. You see 4 more features on the initial curve, initial data. So what is the reason for that? Again, these are the cobalt clusters within the titanium dioxide. And this is cobalt oxide on the surface of the titanium dioxide. And this shoulder on the left side of the peak, as we have explained here, okay, it is due to the lattice expansion of the titanium dioxide, because cobalt atoms are bigger than the titanium atoms, and lattice of the titanium dioxide will be expanded, and due to the expansion, the D parameter within the Bragg's law, this D parameter will increase, then sinus theta will decrease. Then for this reason, we see a decrease in the 2 theta angle of this one. So it means that some portion of the cobalt atoms are also located within the crystal structure of the rutile, and many of them also produce clusters. So you see that how this method is powerful. It gives lots of information. So now let's finish that lecture with in-plane X-ray diffraction. So all these geometries are related to the out-of-plane X-ray diffraction. This is the film, and we send X-ray from that direction, and they are reflected to the detector, okay? This is also called as out-of-plane XRD. But what happens if I send X-rays from that direction? So what do you see here? That the crystals have that surfaces. You see, if you look from that side, you will see that surface and also this bottom surface. But if you look from that side, you will see that surface, and you will see also that surface behind it, okay? So this is the difference between out-of-plane X-ray diffraction and in-plane X-ray diffraction. In out-of-plane X-ray diffraction, as we have discussed here, these are the examples for the out-of-plane X-ray diffraction. These are the crystal planes, okay? And we send X-ray from the X-ray source, and it goes to the detector. And you look to the sample from top. In case of in-plane X-ray diffraction, we see the side planes of the crystals. Okay, these are the side planes of the crystals. So you see diffraction from the side planes of the crystals. So sometimes this gives us very useful information. Here I show you a picture of X-ray diffraction machine produced by Rigaku. The name of the machine is Rigaku Smart Lab. We have it in our university at Gebze Technical University, physics department. Here we have an X-ray source, and these are the optics. These are the optics, and here we have a detector. And can you see that here we have a sample? Okay, this is the sample sample holder, and this is multi-axis goniometer, very useful one, computer controlled, very user friendly. So by using that one, you can carry out both out-of-plane XRD and in-plane XRD experiments by using this guy. And here I have my last transparency. I will show you one example of in-plane X-ray diffraction measurement. So what do you see here? If you have this type of hexagonal crystal structure, and if you look from the out-of-plane direction, okay, from the top surface, you will see this surface and also this bottom surface, okay, and diffraction will be from that planes, okay. But if you use in-plane X-ray diffraction, you will see that plane, you will see that plane, you will see that plane, you will see that plane. If you rotate this one around itself, you can see all planes, and you can see signals from all planes. Look at the hexagonal crystal structure. We have one plane here, second one, third one, fourth one, fifth one, sixth one. We have 6 surfaces on the sides of the hexagonal structure. If you rotate it around itself by using in-plane X-ray diffraction method, you will just rotate the material around itself. Okay, here we have a sample holder. You can rotate the sample. You are just rotating the sample. So you are rotating that crystal. Okay, then you arrange the diffraction condition by using in-plane XRD. And if your diffraction condition is perfect, then you will able to see all surfaces. 6 surfaces. You see, it is very nice signal from zinc oxide, same material, this one, okay, which was also a C-plane or one direction. I mean, the basal plane is on the surface, okay? So then we can see very nice pics from the in-plane X-ray diffraction. This data is also taken in Hamburg at HAZELAB synchrotron radiation facility, I think in 2005 by me and Alexei Nefedov. Do you have any question? So this out of plane X-ray diffraction, you can get information from that planes of the surface. You can see planes from top of the material, but with in-plane X-ray diffraction, you can get information from the side planes of the material. So you can also get information about the material from that view, okay? Very useful, non-destructive method, X-ray diffraction. For this reason, it is widely used in physics, in material science, in chemistry, in biology, okay? For many fields of science and also for technology, this method is widely used. Do you have any question with that part?
Hocam ben bir şey soracağım ama emin olmak için sormak
Of course,
istiyorum.
please.
Biz şimdi D'nin azalmasından bahsettik ya, kobalt atomları
Yes.
çinkonun yerini aldıktan sonra.
Yes.
Ben burada çizebiliyor muyum bilmiyorum ama.
Çizebilirsin.
Ben bile büyük olacak galiba. Yani bu, pardon. Mesela burada kobalt atomları çinkonun yerini aldığı zaman bu küçülecek. Yani şöyle bir şey olacak, değil mi?
Evet, çünkü because the cobalt atoms are smaller than the zinc atoms.
Aşağıdaki de küçülecek. Diyelim ki C plane'de oldu bu.
Evet.
O zaman A artacak. Çünkü yukarısı küçülürse A artmak zorunda. Yalnız
yok, A'nın
formülden dolayı
A'nın da if you are talking about lattice shrinking, okay, you can consider that both D and A, lattice parameter and interplanar distance must be decreased, okay? So look
evet, ama mesela formüle baktığımız zaman 1 bölü D kare eşittir H kare artı K kare bölü A kare artı L kare bölü C kare. Zaten C burada azaldığı zaman L kare bölü C kare artmış oluyor. A artsa bile H kare artı K kareden dolayı o değer daha az.
Okay, Mergim, just think simple, okay? Just consider cubic cell, okay? Let's consider that this is a perfect cubic cell. I couldn't draw it very well. So this is cubic cell. What was the lattice, what was the interplanar distance formula? Lattice parameter. Okay. So at the beginning, you have bigger atoms, let's consider. Okay. So interplanar distance between that surface and that surface is given by that quantity, okay? So what is the lattice parameter? Distance between the atoms, okay? You see like this. If you use smaller atoms, just use smaller atoms. What do you see here? That both the interplanar distance and lattice parameter are decreased, okay? You can also see here that one, don't change the surface. If you decrease this one, this will be decreased. If you increase this one, this will also be increased, okay? So it is same also for hexagonal crystals. If D is decreased, balls, here let me show you the formula of interplanar distance for the hexagonal crystals. This is the formula. The surface is fixed, and if this is decreased, balls, that guy C and A are decreased. Okay?
Sizin slaytlar daha farklı, güncellenmiş galiba. Onları bize gönderecek misiniz?
Yes, I have updated these transparencies, but they do not contain much more information compared to the other ones, the old ones. But if you like, I can send them.
Sure.
Okay.
You would like it.
Okay, any question? Any other question? So thank you for joining us. See you on next week and take care of yourself. Bye-bye.
Thank you.
Take you yourself care to you. You too.
Thank you Murat.
Hadi görüşürüz. İyi cumalar hocam.
Sağ olun size de.
Görüşürüz.
Teşekkürler hocam.
Görüşmek üzere Aydan.